Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you've come to the right spot, so go ahead and hit the subscribe button. That said, let's get into the current video. I'm going to discuss one of the volume formulas from your Calc 2 course where you talk about solids of revolution. And in this particular case, I'm going to look at the washer method when I do a rotation about the x-axis. So first of all, what I'm going to do is kind of talk about the general formula, and then we'll go ahead and do examples. So let's say I have the following setup. Okay, I'm going to have, let's say, two functions. Let's say I've got the function that looks like this, and I'm just going to label that y equal to f of x. And then I'm going to take a second function, let's say this one, which is y is equal to, say, g of x. And the idea is I take the area bounded between those. So I take this entire area bounded between those two graphs on, say, the interval from, I'm not going to write it yet, but say on the interval from, say, a to b. I take that and I spin that about the x-axis, and I'm going to create a three-dimensional solid that has a hole in the middle. And let me see if I can kind of get a general idea of what that would look like. A little squeaky there. So let's say there's the symmetric image of, say, that graph. Not perfect, but hopefully it gets the idea across. And then I'm going to do that. And the idea is, again, I create this three-dimensional solid that's going to look like the following. So I get this three-dimensional solid that has a hole in the middle. Now, the idea is, how could I construct the volume of this? Well, I'm going to figure out a way to sort of decompose this, right? Same thing with the area under the graph in, say, Calc 1. We start, or at the beginning of Calc 2, you start by decomposing it into a sequence of rectangles, creating a Riemann sum, and then you take the limit of that, and then that allows you, and then after that, of course, you use the fundamental thermocalculus. But the idea is I have to figure out how am I going to decompose this into simpler geometric objects. And the way I'm going to do that is by looking at cross-sectional slices of this. And let's say a cross-sectional slice looks like so this cross-sectional slice is going to look like a washer, and that's going to lead again to the washer method. And the idea is I need two pieces of information for that washer. I need the inner radius and I need the outer radius. Notice that the inner radius is going to go from the axis of rotation to the innermost function, or the lowest function. The outer radius is going to go from the axis of rotation to the outermost function, or the upper function. And therefore, I get the following. The volume of this three-dimensional object is going to be the integral. Remember, I didn't write it in there because I didn't want it to look too messy, but the idea is if I go from a to b on the x-axis, that's going to give me a limits of integration from a to b, and then it will be pi times the outermost function squared minus the innermost function squared, and then dx. Okay, so pi innermost function squared minus the outermost function minus innermost function squared. And the idea is that remember, for the disk method, I don't have a hole, so in other words, I don't have this g of x function. You could think of, in that case, that g of x would be 0. That would just eliminate this term. Oh, I guess I'd have to go to the other side of the the window here to cover that up, but pretend that wasn't there, then I would just have pi times the square of the function, which is pi r squared, which is, again, the disk method. So this kind of degenerates down to the disk method in that case. Let's go through now and do some examples. So let's say I take the following. Let me just kind of draw a picture. And I'm going to take the graph from my sort of inner function. Let's take y equals the square root of x. So here's y is equal to the square root of x. And let's say we go from 0 to, let's say, 4, just have a perfect square. And then let's say my upper function is going to be, let's just say, a horizontal line. If this is at, when I plug in 4, this would be a height of 2, so I got to go above that. Actually, I could just go 2, but let's go up to 3. So there's 1, 2, 3. Let's take the horizontal line, y equal to 3. And we'll take that area and we will spin that about the x-axis and we will create a three-dimensional solid. Okay, let's go ahead and compute the volume of that solid. So solution. Volume is going to be, well, again, my limits of integration. Since I have a washer that starts at 0 and I have washers all the way up until 4, that gives me my limits of integration of 0 to 4. And then pi times the square of the upper function. So that would be 3 squared minus the square of the lower function, which would be, of course, root x squared. And then let's see what this gives me. Integral from 0 to 4. Of course, 3 squared is 9, so that would be 9 pi. And then square of root x is x. And then multiply that by pi gives me negative pi x dx. Now, relatively speaking, that's a pretty trivial integral once you are in this portion of your Calc 2 course. Notice that I mentioned before that when you are doing these exercises, it's the setup that is the more challenging portion, kind of decomposing the geometry of the solid, figuring out what method, disk, washer, shell, is appropriate, and then figuring out what's the radius, what's the limits of integration, shell method, what's the height, what's the radius, all those different things. What if I rotate about the x-axis, the y-axis? There's all those different variables that, kind of add to the complexity of it. Generally speaking, the integration itself is kind of the easier part. Again, just generally speaking. Let's go ahead then and integrate this. Antiderivative of 9 pi minus pi x would be 9 pi x minus pi x squared over 2, and I'm evaluating from 0 to 4. Plug in my lower limit of integration, of course it's 0. Plug in my upper limit of integration, 9 times 4 would be 36, so I get 36 pi minus, again, if I plug in 4 here, I would get 4 squared, which is 16. 16 over 2 would be 8, so I get minus 8 pi, and 36 pi minus 8 pi would give me 28 pi. One more sort of analysis of these numbers here. The 36 pi is, well, what if I just use y equal to 3 with the disk method, and I did the root x with the disk method? So I said that the volume of this was going to be the volume of the outer function minus the volume of the inner one. That's where I would get the 36 pi minus 8 pi, and then you get 28 pi. So you could get the same thing if I did sort of the disk method and then subtracted the 2. Of course, that's literally what this is. All right, let's do one more example. Okay, so let's say we were going to take, here's the graph of y is equal to 1 over x, And let's say my upper function is going to be y equal to x. Of course, the intersection point there would occur at 1. So let's go from 1 to, let's say, 3. So I'm going to take this wedge shape right here. I'm going to spin that about the x-axis and then compute the resulting volume. Okay, so let's go ahead and do that. All right, volume would be integral. Now my limits of integration, the washers would be stacked horizontally. That means my limits of integration are going to go from 1 to 3 because I have a washer for each x value between 1 and 3. Okay, so 1, 2, 3, and then pi times the first thing that I put in there is the square of the uppermost function, which would be x squared minus, then I'm going to do the square of the lowest function or innermost function, however you want to say it for this particular shape, giving me 1 over x squared dx. Okay, so again, there's the setup for the computation for the volume. So now let's go ahead and compute this integral. Okay, this will give me equal to. Now over here, I just distributed pi through. Of course, that's perfectly fine. Another property of integrals, I could take that constant and pull it out front. So I'll do that here for no particular reason, just to again emphasize that I can take constants and pull them back and forth. And then I'd have integral from 1 to 3. Now, of course, I could directly integrate x squared, but I'd like to do them at the same time. So I'm going to rewrite x squared here. And as a reminder, when I take a square of a fraction, of course I square the top and the bottom, which would be 1 over x squared. And then to find the antiderivative, I want to write it as x to a power. That means I'm going to write this as negative, of course that's this negative, x to the negative 2 dx. So x squared minus x to the negative 2 dx. And then again, the reason for doing that is it's just easier to think through the power rule. Right, for antiderivatives where I add 1 to the exponent and then divide by the increased exponent. Okay, so let's go ahead then and evaluate this. I get pi times antiderivative of x squared, x cubed over 3, antiderivative of x to the negative 2. Now let's just kind of carry this negative along here. I'm going to increase the exponent by 1, so negative 2 plus 1 would be negative 1. I then have to divide by the increased exponent, which would be negative 1. Of course, that's going to become positive, but let's do that in the next step. So that's divided by negative 1, and then there's my antiderivative, and I have to then evaluate this from 1 to 3. Okay, now to evaluate this, let's clean this up first. So negative and negative is going to be positive. X to the negative 1 would be 1 over x. That gives me pi times x cubed over 3 plus 1 over x, evaluated from 1 to 3. Okay, I would get pi times, if I plug in 3, I'm going to get 3 cubed. Of course, it's 27, but let's think of it as 3 cubed over 3 because a factor of 3 cancels, giving me 3 squared, which is 9, plus 1/3. And then it'd be that minus, if I plug in 1. If I plug in 1, I'm going to get 1/3 plus 1. Okay. And then if I distribute the negative through here, notice I would have a positive 1/3 minus a 1/3, which is going to cancel. And then I'm going to get 9 minus 1, which is 8, giving me a total of 8 pi for the volume using the washer method. Okay, thank you for watching, and please consider subscribing.